sound wave that exists in a tube of air. When we studied the wave on the string, the key was to realize that since both ends of the string were fixed, each end has to be a node of the oscillation, because there was no amplitude of oscillation at either end. This is called boundary condition. That's what happens at each end of the string. What we have here is a similar situation, except the medium is no longer string, but rather it's air. Consider a tube with one end closed and the other end open. Now suppose there is a sound wave propagating into it. What happens when it meets this closed end? Well, this acts like a wall, so it bounces back, right? So you got one wave going in, another wave bounced back. You got two oppositely traveling waves, and of course the result is a standing wave, just like on the string. Okay, so what we have is a standing sound wave. What we need to know is what are allowed frequencies and wavelengths that can exist on this pipe. To figure that out, we use something similar to the case of a string, the wave on a string. That is, let us take a look at what happens to the sound wave at those two ends. Okay, now you know from the previous chapter, the physical nature of the sound wave can be understood either as a pressure wave or as a displacement wave, right? You think of the pressure wave because the pressure of air due to the presence of sound is no longer uniform throughout. Rather, on top of the ambient pressure, there's a slight variation of air pressure that propagates like a wave. Okay, so that is called pressure wave. The reason why there is a pressure modulation, there's a pressure wave, is because as the air molecules move back and forth, they cause air to be locally compressed and locally decompressed. Where the air is locally compressed, you have slightly higher air pressure than the surrounding, and when the air is locally decompressed, you get a slightly lower air pressure than the surrounding. Okay, so you can also think of the sound wave as a displacement wave. Here the displacement refers to molecular displacement. Okay, so we're looking at the collective motion of molecules going in like this or going out like that. Okay, if they go in like this, that creates a local high value of pressure, and if they go out like that, that decreases local pressure. There is a relationship between the pressure variation and the displacement S of the sound wave. This equation is copied from the last chapter. Here, B, as you recall, is the bulk modulus. Okay, you notice the interesting thing here, and that is delta P, the pressure wave, is not directly proportional to the displacement wave S. Rather, is directly proportional to the derivative of S with respect to location. Now that sort of makes sense. Okay, now what that means is that if this is a sine function, if S is a sine function, delta P is a cosine function, they differ from each other by a phase of 90 degrees. So when one of them is 0, the other is actually maximum. How does that make sense? Well, because imagine if the air moves in like this, right? They move in like this. Of course, that's going to create a local higher value of pressure, so you get a pressure antinode. Okay, but as the air come in, they are compressed towards each other. They got no place to go, so the displacement is actually 0. Okay, so you have, in this case, 0 displacement, but great amount of pressure. So indeed, when one is a sine function, the other is a cosine function, qualitatively that makes sense. Okay, so let's take a look at the pressure or the displacement wave of the air column due to the sound produced as a standing wave inside this fluid, inside this tube. First of all, let's look at what happens at the closed end. Now, it is clear that at the closed end, the movement of the air molecule due to the sound is like this, right? But when they hit this wall, they got no place to go, right? So what is the displacement of the longitudinal air wave S at that location? Well, they wanted to go this way, but they cannot because a wall stops them, so S is 0. Okay, so this obviously is a node of the displacement. Node of displacement. All right. What about pressure then? Well, the pressure, according to this expression, if this is a node, then that would have to be an antinode. And that makes perfect sense because what that means is that the air molecules are congregated here. Okay, once the air molecules come in like this, they got no place to go, so they all stopped here. They all trapped here. There is a local, of course, increase in the density of the air molecules. That, of course, increases the pressure at that region. So you will have a pressure antinode at this location, yet a displacement node. Okay, when I use node here, I'm assuming that I'm treating this as a displacement wave. Please do not confuse it with pressure wave. They're equivalent to each other, but if you want to think of this as a pressure wave, that this is an antinode. Okay, it is a maximum value of the pressure. Now, what happens at the open end? Well, at the open end, the air pressure here is linked to the air pressure outside, right? Because it's exposed to the air outside. So you can imagine, you don't really have a lot of variation of air pressure air pressure here. The air pressure pretty much is just the ambient pressure. So this would be a pressure node, and therefore it's a displacement antinode, which means the air movement is the largest. That also makes sense because, after all, the air molecules, when they reach this region, they're open to the air outside. Of course, they can move freely. Okay, so this is a displacement antinode, and the closed end is a displacement node. Okay, knowing this will greatly help me draw schematic diagrams for the resonance that can exist in this tube. The idea here is that when you draw displacement waves, you have to make sure this closed end is a node and this open end is an antinode. Okay, so let me draw a few possibilities. Okay, so I have here a tube with one end closed and that end open. Let us draw the displacement air waves due to a presence of the sound. Okay, again, this would be a node, it's a closed end. This would be an antinode. So one possibility, which corresponds to the largest possible loop size, would be something like this. Right? After all, you have a node here and antinode there. Okay, now if you draw something like that, then you realize this is only half a loop, right? Because if I extend the other half, I get a whole loop, right? So the length L in this case would have to be only half a loop. Now, how long is each loop in terms of wavelength? We learned that is half a wavelength, so this is actually lambda over 4. Okay, in other words, this wavelength is 4 times the length of the pipe. We call it lambda 1. That is the longest possible wavelength. Okay, lambda 1. So lambda 1 equals 4L, and what is the corresponding frequency? Well, the longest wavelength corresponds to the lowest frequency, right? So what's F1? This is the fundamental mode, or the first harmonic, corresponding to the lowest frequency that can exist in this pipe. That would be V over lambda. V is the speed of sound in air over lambda 1. Okay, now lambda 1 again is 4L. Okay, so that would be V over 4L. Fundamental mode. Now, next, let's draw another possibility. Again, we want to keep this end a node and this end an antinode. So how about something like this then? All right, now, right, that works too. Node and an antinode. But this time I have squeezed in 1.5 loop in between the same length L. And therefore, I say L equals, this time, 1.5 loops. In other words, 3 over 2 loops. And you know each loop is half a wavelength, so this will be 3 over 4 lambda. And that is the wavelength for the second harmonic, or lambda 2, and that allows you to find F2, the second lowest frequency that can exist in this pipe, and that would be V over lambda 2. So what is that equal to? Well, actually, you see lambda 2 is 3 times as short as lambda 1, so therefore this would be 3V over 4L. Okay, and you notice this really is just 3 times F1, right? 3 times F1. Okay, let's keep on doing this. We make the loops even shorter, so this time I'm going to include 2 full loops and then plus half a loop at the end. I must have a half loop at the end because I want an antinode at the open end. Okay, so this time what do we have? Well, this time L equals 2.5 loops. Okay, and so that's 5 over 2 times lambda over half a wavelength. That is lambda 3, right? And so the corresponding frequency, f3, what's that equal to? Well, that would be 5 times f1, right? So this would be 5v over 4L, and so on. Okay, you get the picture. You got the lowest frequency, a fundamental frequency, and the second harmonic is 3 times as high in frequency. The third harmonic is 5 times as high, and so on. So in general, what kind of frequencies can you produce on this pipe of length L with one end closed, the other end open? That would be F equals to Fn, okay? 1, 3, 5, so in general it's 2n plus 1, right? 2n plus 1. V, speed of sound, over 4L, okay? N equals, the lowest n is 0 because, you know, that would be, you have a 1 left, that's corresponds to the lowest frequency, 0, 1, 2, and so on. Okay, this is how we can use a pipe of a certain length to select a frequency we want to produce. You see, the frequencies that can exist on this pipe depend on 2 things, okay? One is the speed of the sound, the other is the length of the pipe. So by choosing the length of the pipe, we can figure out what kind of frequency that can be produced. Again, the key here is to make sure you know the closed end is a node and the open end is an antinode. You know, you don't have to remember those formulas mechanically. All you need to do is to understand what happens at the boundary, okay, closed end, open end. Then you can just start to draw these pictures, right? And then you get a whole bunch of loops, and each loop is half a wavelength. That allows you to figure out the wavelengths, and once you know the wavelengths, you can go ahead and figure out the corresponding frequency. Now, what if I change the situation at the border so that this time I have both ends open, okay? Instead of a closed end and open end, I have both ends open. This would correspond to a flute. Okay, so here is a situation like this. You have your playing a flute, okay, and this flute has both ends open now. You look at this structure here. This structure is for you to blow air in, okay, just to blow air in so that you can start a vibration, okay? That's all there is to it. But essentially, see, this is open to the outside, right? So this is an open end. This is also an open end. Remember, an open end corresponds to an antinode of displacement. So you must make sure this is an antinode, this is an antinode, right? And how do you draw something like that? Well, this will give you the longest possible loop, right? You get antinode, antinode, of course, there's a node in the middle. And here is the next possibility. You have an antinode here. So you see, the idea is you must have a half loop at each end, okay? And in between, you can put in 0 loop, 1 loop, 2 loops, 3 loops, whatever you want to do. Okay, now, what about the corresponding frequencies? Well, this is half a loop, this is half a loop, I'm sorry, yeah, this is half a loop, this is half a loop. So you add them together, you get 1 loop, right? Now 1 loop, what is the total length? Okay, the total length is L, and that also equals half a wavelength because it's 1 loop, right? So you see, L equals lambda 1 over 2 because it's half a loop. I mean, this is half a wavelength for 1 loop. So that gives you lambda 1, which is 2L, and that allows you to find F1, which is V over lambda 1, V is the speed of sound. Okay, that is V over 2L. So this is how you find the first harmonic that can exist on a pipe with both ends open. Okay, here is the next mode. You put in a whole loop in between this half a loop at the end and that half a loop at the end. Okay, so what you have here is half a loop plus 1 loop. You have a total of 2 loops instead of 1 loop, so you cut the size of the loop by half. Therefore, lambda 2 instead of 2L now becomes 1L, okay? 1L. And from that, you can find the frequency. That frequency turns out to be twice as much as the first harmonic because, you know, the wavelength is halved. Okay, so here's the second harmonic. And they have the third harmonic and so on. You can do this calculation. Turns out the third harmonic is 3 times in frequency compared with the first one. Okay, so this is when you have a loop with both ends open. Here again is a situation that we discussed earlier, except this time the drawing is more professional. This is actually a real pipe. you have one open end, one closed end. The open end is shaped like this so that air can flow in. Okay, so this is an open end. Again, you have a node at the closed end for displacement, and an open end at the open end, and so on. The calculation goes like what we had before. And you notice the interesting thing here, just like we discussed before, the third harmonic is 3 times in frequency as the first one, and the fifth harmonic is 5 times in frequency as the first one, and so on. Okay. Now, what if both ends of the pipe is closed? Well, if you manage to get an air vibration inside with both ends closed, this time both ends must be a node of the frequency of the sound wave displacement. So you have it's something like this, okay? Right? Both ends closed. Or you can have something like this. Or you can have something like this. You get a picture, right? So the first harmonic would correspond to half a loop. Second harmonic would correspond to 2 loops, and then you have 3 loops, and so on and so forth. You notice that this really has the same mathematical formula as the case when both ends are open, right? Except when both ends open, you have to draw it slightly differently, like this, right? And you draw it something like this, and you go something like this, right? But if you add the total lengths, okay, here is 2 half loops forming 1 loop. Here is 2 half loops plus 1 whole loop. That's 2 loops. Here is 2 half loops plus 2 full loops plus 2 half loops. That's 3 loops, just like this, right? So with both ends closed, the formula for the frequencies and the wavelengths will be actually the same as the case when both ends are open. So you see, you don't have to memorize these formulas mechanically once again. You just have to know 2 things. First of all, what happens at the closed end and what happens at the open end. And then you just have to draw the these diagrams for nodes and antinodes and make sure that you know that each whole loop is half a wavelength, each half a loop is a quarter of a wavelength. Okay, so from that we would know how to choose the frequency that can be produced by a column of